Welcome to AP Calculus AB video for skill number 147. I can use logarithmic differentiation. And featured below are the 5 orders of columns and the capitals that they have in each order. I've spoken of Doric, Ionic, and Corinthian. You can see that the key difference between the Doric and the Tuscan order is that the Doric has the flutings in the column. The trivia question for the day is the 5th order. What is the name of this order? Alright, today we're going to learn about logarithmic differentiation, and the purpose of this is to solve some sort of complex derivatives. For example, if I wanted to find what is the derivative of x to the x. I don't know whether I'm supposed to use the power rule or exponential rules there, or some sort of combination of the both. And we actually use logarithmic differentiation to solve that problem. And before we get into logarithmic differentiation, it would be good to freshen up on some logarithmic rules. So the product rule says that if I have, I'm going to do all these as natural log. If I have the natural log of a times b, I can rewrite that as the natural log of a plus the natural log of b. And of course this would work for any logarithm base, but for logarithmic differentiation we tend to stick to the natural log base. Our quotient rule says that if I take the natural log of a over b, then that is going to be equal to the natural log of a minus the natural log of b. And then finally my power rule says that if I have the natural log of a to some power, that is the same as saying power times the natural log of a. So we're going to use these 3 rules extensively in logarithmic differentiation. And then a quick review: if we want to take the derivative of the natural log of u with respect to x, that's going to be 1 over u times du dx. That's the chain rule right there. So let's take a look at when we want to use logarithmic differentiation. So logarithmic differentiation is good to use when you have either functions which would require multiple iterations of the chain rule, product rule, and quotient rule. For example, this thing is quite nasty looking. You can see that we have a quotient, and within that quotient we have a product, or another product here, and within that product we have the chain rule. And so using those 3 things, we would actually create a nightmare of problems to track. So we use logarithmic differentiation, which actually makes it a lot easier to find the derivative of this. Another time you're going to use logarithmic differentiation is if you have a function being raised to a function. So what we have here is something a lot like what I started out with this x raised to the x. So I've written down the steps here, steps 1 through 5, on what we should do, and we're going to use those steps on the next page as we work through logarithmic differentiation. Before we look at the next page, I just wanted to use this on a pretty straightforward problem, a lot like the ones on your worksheet. This one, x to the x. So if we have y equals x to the x, and we wanted to use logarithmic differentiation, the first thing we do is we take the natural log of both sides. So the natural log of y is equal to the natural log of x to the x. Then we're going to use step 2, which says apply log properties, product, and quotient. And we only have one logarithm, so there is no product or quotient to do. But we can use the power rule to remove the exponent. So we can move this exponent down in front. So what we have is the natural log of y is equal to x times ln of x. Step 4 says use implicit differentiation. So when we take the derivative of the left side, we get 1 over y dy dx. And when we take the derivative of the right side, we actually have to apply the product rule. So the product rule tells us the derivative of the first times the second plus the first times the derivative of the second. From there, what we want to do is solve for dy dx. So dy dx is equal to y times, let's just simplify this, y times that value. And then we can substitute y back in. And since we knew y was x to the x, our dy dx is equal to x to the x times the natural log of x plus 1. And there we have it. Logarithmic differentiation with a simple power problem. Okay, so I've got y equals 3x squared to the x to the fourth, and we want to use logarithmic differentiation. So step 1 says we take the natural log of both sides. So I can write this as the natural log of y is equal to the natural log of 3x squared to the x to the fourth. The next step says apply laws of logarithms for the product and quotient. And in this case we actually don't have any of those laws to use. So step 2 we don't need to do on this problem. But step 3 we would do something with. It says apply the laws of logarithms power to remove exponents. So we're going to apply the power property. And we see that what we have is a exponent right here. So we could rewrite this as the natural log of y is equal to x to the fourth times ln of 3x squared. Step 4 says use implicit differentiation to find dy dx. So if we're going to find or use implicit differentiation, we're going to start by taking the derivative of the left side. So the derivative of the left side is 1 over y times dy dx, and that's our implicit differentiation. The derivative of the right side is actually going to require us to use the product rule because we have two pieces. So the derivative of the left times the right plus the left times the derivative of the right. And if we take the derivative of natural log of 3x squared, we're going to get 1 over 3x squared times 6x. And because we're solving for dy dx, we need to multiply the y to the other side. So we have dy dx is equal to y times 4x to the third ln of 3x squared plus, if I simplify this all out, I get 2x to the third. Finally, in step 5 it says substitute the known value of y to write the derivative in terms of x. So our derivative in terms of x, we know that our y was 3x squared to the x to the fourth. So we write 3x squared to the x to the fourth, and we multiply that all by 4x to the third ln plus 2x to the third. Alright, there we go. There is logarithmic differentiation, and as you saw, one of the steps in logarithmic differentiation was implicit differentiation. Let's look at another example. Before we go to the next example, which is a little bit harder, I wanted to do logarithmic differentiation on one that is fairly easy. So let's just do x plus 1 to the third over x squared minus 2 to the fifth. Now, of course, we could use the quotient rule with the chain rule on the inside, but I wanted to show logarithmic differentiation here. So step 1 tells us to take the natural log of both sides. And we get x plus 1 to the third over x squared minus 2 to the fifth. Step 2 says use the product or quotient rules to split up your logarithm. So our logarithm we see is a over b, so we can split that into two logarithms, x plus 1 to the third minus the bottom. The next step tells us to apply the power rules of logarithms. So we can move these exponents down to the front. Ln of x squared minus 2. Right. The next rule tells us, or step tells us to take implicit differentiation of both sides. So the implicit differentiation of the left. For the right, we get 1 over x plus 1 times 1. And then for the bottom one, or the next one, we get 1 over x squared minus 2 times 2x. And finally, we move y over to the right-hand side, equals y times 3 over x plus 1 minus 10x over x squared minus 2. In the end, we want to substitute our y value in. So we get a final answer of dy dx is equal to x plus 1 to the third over x squared minus 2 to the fifth times this quantity. All right. There we have it. Implicit differentiation used within the process of doing logarithmic differentiation. So here we have what looks like a lot of chain rule and product rule inside, and so we are going to use logarithmic differentiation. And step 1 says take the natural log of both sides. So we can take natural log of the left is equal to the natural log of the right, x squared minus 4 to the fifth, all over, and I'm going to go ahead and write this as a fractional exponent. All right. Step 2 says apply laws of logarithms, the product and the quotient rule to break it up. So what I can do is I can break up my right-hand side to be 3 logarithms. We have the logarithm of 2x minus 7 to the third, and we're going to add the logarithm of x squared minus 4 to the fifth, and then we'll subtract the logarithm of x squared minus 4 to the 1/2. There we applied our product and quotient rules for logarithms. Step 3 asks us to apply the laws of logarithms, the power laws. So that means we're going to be taking our powers and moving them down in front. So we get the natural log of y is equal to 3 ln of 2x minus 7 plus 5 ln of x squared minus 4 minus 1/2 ln of x squared minus 4. Alright. Step 4 says use implicit differentiation to find dy dx. So the derivative of the left is going to be 1 over y dy dx. The derivative of the right will be 3 over 2x minus 7 times 2 plus 5 over x squared minus 4 times 2x minus 2x squared minus 4 times 2x. Alright, then we have to multiply the y across. So we get dy dx is equal to y times, I'm going to start simplifying these, 2x minus 7 plus 10x over x squared minus 4 minus 2x over 2 times x squared minus 4. The final step asks us to substitute the y back in. So we can rewrite the y, which was this value right here. 2x minus 7 to the third. Let's just shrink this down. There we go. So dy dx is equal to 2x minus 7 to the third, x squared minus 4 to the fifth, all over root x squared minus 4 times this piece. All right. In looking back at this problem, I actually realized that we can take these two pieces and combine them if we wanted to. And in truth, that's something that a very observant student might have picked up very early on, as we could have combined those before we even started the process. In the end, it doesn't matter because we still arrived at an equation that tells us what dy dx is. Alright, hopefully by now you know how to use logarithms or to do logarithmic differentiation. And what we have here is the fifth order, which appears to carry the volutes of the ionic order and the acanthus leaves of the Corinthian order. So it's kind of a composite of those two, which gives us our clue that it is the composite order.